Hello, so today we're going to do some more proving trig identities to be true. So we are trying to take one expression and show that it is equivalent to another expression. So these are things we don't know are equal yet, so we can't treat them like equations with adding and subtracting to both sides. We can just replace things. That's our first strategy, is look for things to replace. We're trying to turn something there into something else. Generally one side is more complicated. It's often the best idea to start with the complicated side and try and simplify things. Sometimes you have to get messy before you can get clean though. Alright, my number one strategy. This is not always true, there are other times, but when in doubt, turn everything into what it means in terms of sine of x and cosine of x. This is a go-to strategy that works. Now there are times when this will make things way more complicated than you want, so you have to look and keep in mind some other strategies like thinking about the Pythagorean identities. Sine squared of x plus cosine squared of x equals 1. When we have things squared. Now that's not always true when we have things squared, but particularly when we have things squared and adding a number, a 1 or a 2. If you're adding a number and you have sine squared of x, or subtracting a number and sine squared of x, those are times you want to think about those Pythagorean identities instead of just turning things into sine of x or cosine of x. Other things to do, if one side has two fractions in it and the other side is just one fraction, you're going to have to add your fractions on that side to turn it into one fraction. We want to simplify fractions, so canceling will be big. Canceling is huge, but you have to be careful when you cancel. Again, you cannot cancel over adding and subtracting, only over multiplying. You can cancel factors. You can cancel when you are multiplying by 1, not adding 1. Multiplying by versions of 1 is one of the things we do up here when we are trying to add fractions. When we need a common denominator, it is often good. We get our common denominator by multiplying by some fancy version of 1. And that's what I have. And then in general, you want to think about, you are leaving a roadmap for somebody else to follow, right? So you want your steps to be clear. You also want to keep in mind where you are going. If you're taking a trip to Duluth, you want to make sure the whole time you're thinking about, I need to get to Duluth. Otherwise, you could end up in Madison or Florida or Canada, right? You have to keep your destination in mind. It's a good idea to check in periodically. Am I headed toward where I need to go, or am I on some side track? So let's try a few. Those top 8 identities you need to get memorized. And again, the most important of the Pythagoreans, like these guys you should have. These ones are fairly simple. Sine of x is your opposite over your adjacent. So if you forget, that's the way to think about that. And then if you have this one, you can get the other two by, in the first case, dividing everything by cosine squared of x, and in the bottom case by dividing everything by sine of x. So if you remember that first one, you should be good. All right, so let's actually try to do an identity here. So we have 1 plus cosine x, 1 minus cosine x. So I'm going to actually FOIL. Because over here I don't have any addings and subtractings or any even multiplyings. Well, you do have a multiplying, but it's to a power. So we're going to FOIL. So I take first times first. I get 1. I'm going to get a minus 1 cosine x. I'm going to get a plus 1 cosine x. And I'm going to get a minus cosine squared of x, right? And I would like that all to equal sine squared of x. Okay. What I get out of here, this middle is going to disappear, and I'm left with 1 minus cosine squared of x. All right. Now that looks sort of familiar. It looks like our Pythagorean identity. It is not the identity exactly, but if I think about solving this equation right here for sine squared of x, I would subtract cosine squared of x from each side, and I can do that up here because that is an equation. I know those two things are equal, so I can treat it like an equation and do the same thing to both sides. I cannot do that down here because I don't know for sure. There's really a big question mark. Is this the same? I don't know. So I can't treat it like an equation up there. But so I know from up there that sine squared x is sine squared x. You are done when I've turned the complicated side into the other side, when both my sides are the same. And sometimes we can work the simple side back a little bit if that helps, if we're getting stuck. Okay, So here's another one. Show that cotangent of alpha, tangent of alpha, sine of alpha, plus cosine of alpha is cosecant of alpha. And we're going to use all sorts of different variables. You shouldn't be afraid of them. It is important that you actually have a variable. I don't care if you turn it into a different variable, but then you must use that variable throughout your whole problem. Okay, so you need to be consistent in your variable, and you need to have variables. They are important. We have to take the cotangent of an angle. Cotangent has no meaning without an angle attached to it. All right, so on my first step here is I'm going to do some distributing. I see this as a front and a back. I mean, you may go to the strategy right now of turn everything into sines and cosines. That's fine. I generally like to distribute. Cotangent of alpha, tangent of alpha, sine of alpha, and then my back is going to have a cotangent of alpha, cosine of alpha. And I would hope that that all equals cosecant of alpha. Okay. Now, I like to tell my students almost never, ever, ever use that one right there. In fact, most of the time I'm like, just forget that's there because it will lead you down a wrong path more times than not. However, the one time you do want to use it is when you have cotangent times tangent, right? So because then it's helpful. I can say this is 1 over tangent of alpha, and I have tangent of alpha over 1, sine of alpha over 1. This I'm going to start doing some turning. Cotangent is cosine of alpha over sine of alpha, right? From this right up here, right? And then times cosine of alpha over 1. And I hope that all equals cosecant of alpha. And what's nice about this is in here with the multiplying, notice multiplying here and here allows me to cancel. And if you don't see that, you could also have turned everything into cosines and sines. It's similar. Cotangent is cosine over sine, and tangent is sine of alpha over cosine of alpha, and I still have my sine of alpha. And again, in this part, I'm going to have that canceling, right? Same idea. Either method is okay, right? So I don't care which one you use, cosine alpha over sine of alpha, right? Let's hope that equals cosecant. All right. So now, if I think about this part being gone, I am left with like this over. And I have two separate fractions on my left side, and on my right side, I have one fraction. Ooh, I almost committed the cardinal sin of using two different variables. Different variables would be very bad. I want to combine this and this into one fraction. To do that, I need a common denominator, which I do not have. This has a 1, this has a sine x. So I need a sine x over here. Now I can't just multiply by sine of x on the bottom. That changes my fraction. What I can multiply by is 1. And my version of 1 is sine x over sine x. So over here, I have sine squared alpha over sine alpha. Now don't go canceling because we want it like this. And over here, I have cosine squared alpha over sine of alpha. And notice that I have the squared goes in the middle, right? This over here, sine alpha squared, is squaring really the alpha and not the sine. So not the same thing. I have common denominators. I can get one fraction. And I'm going fairly small steps. You may see right from this step, oh, sine squared theta or alpha plus cosine squared alpha is 1, and you may jump right to this next step, which is 1 over sine alpha. So cosecant of alpha, and then I'm finally done when I make my last statement. It's not enough to end with a true identity. You need to have both sides look exactly the same. So if you stop here, you have not gone far enough. I like to say, you've given me directions to Duluth, but you have not taken me to my hotel. I don't know where my hotel room is, so I'm really close, but this is, boom, I'm in the hotel room, probably in my bed, hopefully sound asleep, or not, having fun, maybe having fun. Okay. And again, if you got stuck somewhere up in here, you could think about somewhere in here that, oh, this is 1 over sine alpha. That's where I'm headed. And then knowing that I have these sine alphas on the bottom is a good sign because it tells me that I'm headed toward something that I need, which is a sine of alpha on the bottom. So you want to keep those things in mind. Keep your destination in mind. All right, so here's another one. One fraction on one side, not a fraction on the other. And I see, ooh, they even have the same thing, which seems tricky. So in my mind, I see things squared, and I'm like, huh. I mean, you know, cotangent squared, I could write it as cosine squared over sine squared, but I also think about, here's this 1 minus. That puts in my head Pythagorean. And the Pythagoreans only work with the something squared. And if I go up here and I think about, if I subtracted sine squared x from both sides, 1 minus sine squared x would be equal to cosine squared x. And it's generally a good idea as much as you can to get rid of adding and subtracting whenever possible. So this becomes cosine squared. This is the Greek letter for beta. And then cotangent squared beta. I would like that to equal sine squared beta. All right. Now I am going to turn everything into sines and cosines. And I'm going to have a fraction and a fraction, so I'm going to write the top as a fraction and the bottom as a fraction. All right, keeping in mind, I want to get rid of everything but the cosine. This seems promising, because what I'm going to do, fraction divided by a fraction, you multiply by the reciprocal of the bottom. And really, I'm multiplying both the top and the bottom by that. This is really another version of I'm just multiplying by 1 or putting in a 1 costume, because what happens on the bottom, those go away. And actually on the top, kind of nicely, that's going to go away. And I'm left with, ta-da, sine squared beta is sine squared beta. Right here, I want you to write it one more time. Again, this up here, you are not at your hotel room. You are not all the way done. Here I am done. All right, let's try another one. Secant x over cosine x, cosecant x over sine of x. A couple ways to start. One is to think, let's get a common denominator. But I think I might first turn everything into sines and cosines. Well, yeah, I don't know. Let's see what we get. So if I do 1 over cosine x over 1 plus. Also, your signs are important. Don't lose adding, subtracting, those things. Cosecant of x is 1 over sine of x. That's all over sine of x over 1. And hopefully that's going to equal secant squared x, cosecant squared x. And it's not bad to have sort of in your back pocket that I know this, if I had this 1 over cosine squared x, 1 over sine squared x, I would be home, right? I'd have the same thing. So that's, my destination is really secant squared x, cosecant squared x, but this would be a good destination also. If I could get here, it's just one quick step to that final destination. All right, so fraction divided by a fraction. And I'm dealing with these two fractions separately. So this, I'm going to multiply top and bottom by the reciprocal of the bottom. Ooh, let's try reciprocal. I'm not multiplying. My version of 1 is going to be, all right, reciprocal of the bottom. Wow, I'm having trouble. Let's try it down here. 1 over cosine x. There we go, which means on the top I need to multiply by 1 over cosine x. Because this is now gone, right? And over here, I'm going to do something similar, but with 1 over sine x. Boom. And I get on top 1 over cosine squared x plus 1 over sine squared x equals secant squared x cosecant squared x. So now I still have two fractions. I need one fraction, common denominator. Easiest common denominator is to have the two things multiplied together. So I can actually make a little space in here for doing that. Right? So what I want, this guy needs a sine squared x, so I'm going to multiply by that version of 1. And this guy over here needs a cosine squared x. Right? And I am left with my top is sine squared x over here. My top on this side is cosine squared x all over my common denominator of cosine squared x sine squared x. And I'm hoping that that is secant squared x cosecant squared x. And again, if you're getting stuck, you want to think about, where am I headed? Where am I headed? Am I going in a good direction? Well, if I remember that I said this is the right side, I see that my bottoms are actually the same. That is awesome. And it would be awesome if my top could turn into 1. And if I go up here, cosine squared x plus sine squared x is in fact 1. So I can take sine squared x plus cosine squared x. The order of adding doesn't matter. 1 over cosine squared x sine squared x. And then that is indeed secant squared x cosecant squared x. And voila, I'm at my destination. Okay. I think we'll try one last one before we send you on to be ready for tomorrow. So here I have FOILing, and you have to remember, this is sort of tricky. You do not just square the front and square the back. We are multiplying by itself. And it's really easy to fall into the trap of, well, I square sine and I square cosecant and then I'm done. But no, there's a middle term. So if we FOIL sine squared theta minus sine theta cosecant theta, another minus cosecant theta sine theta, and plus cosecant squared theta. All right. Now I might want to combine these. These are like terms, but actually it's going to be easier if I go right here into sines and cosines. And if you think about sine theta minus or times cosecant theta being 1, oops, that's fine. Otherwise, if you turn them into their reciprocals, you can see that. So cosecant is 1 over sine theta. Sine theta over 1 plus. And if you have a 2 of them in the middle, you're just going to get a 2. Sometimes it's actually better not to simplify too much, too early. Because now I get sine squared theta minus 1 plus cosecant squared theta. And at this point, I need to think about my destination. Where am I headed? I need a negative cosine squared and a cotangent squared. Okay, so let's stop and take a minute and think about, am I close? Well, I'm thinking, here I got ones and things, so Pythagorean identity. Let's try and figure out what would that be and what would that be using our Pythagorean identities. Okay, so if I come up here, sine squared theta minus 1. If I subtracted 1 from both sides, right, and subtracted cosine squared, I would end up with sine squared x minus 1 equals negative cosine squared x. And that is very helpful because I want negative cosine squared x right there. So this, let's change colors on this guy. This right here is indeed that. So there's my replacement. Negative cosine squared theta. Similarly, if I think about the cosecant squared cotangent squared, what is it that I have again? I kind of forget. Negative 1 plus cosecant squared. So I want my cosecant squared to be positive. If I subtract 1 from both sides, so that's true, I can replace cosecant squared x minus 1 or negative 1 plus cosecant squared x with cotangent squared x. Right? So this becomes plus. And this minus, remember, is part of it. So it's plus cotangent squared x, and I am done. I am in Duluth, or at my destination, all the way to the hotel room. Both sides look exactly the same. So hopefully now you have enough information to be ready for doing some proving yourself tomorrow.